Hi, in this video we are going to talk about cycle detection in the main, so let's get started. What is cycle detection? I think cycle detection is quite intuitive. We would like to detect cycles in a directed graph. It's very important that we are going to deal with cycles in directed graphs, so we have directed edges. And sometimes cycles are good, but most of the times we don't like cycles. For example, cycles are good when we are looking for arbitrage situations on the forex market. Here in these kinds of situations, these kinds of cycles are exactly what we are looking for. This is how we are able to make riskless money. So sometimes cycles are good, but most of the times we would like to avoid them. So operating systems, for example, can have several processes, and there may be some cases, some situations when there is a cycle. These processes are waiting for each other. For example, we have a process A, which is waiting for process B. The B is waiting for process C, and the C is waiting for process A. It's kind of a deadlock situation. So the operating system is going to freeze. So we would like to avoid cycles in order to prevent operating system freezes. So this is the pseudocode basically for the cycle detection. We are going to do it with the help of depth first search, but instead of having a single Boolean flag whether a vertex is visited or not, we have to track whether a vertex is being visited or not. And we just have to consider all the neighbors, and it is a recursively implemented depth first search basically. At the end we have to set the visited to be true and set being visited to false, but what's very important as far as cycle detection is concerned, that if we visit a vertex while this v, so the neighbor, is being visited, then we know for certain that there's a backward edge, so there's a cycle in the graph, so we have to return. Okay, so let's see a concrete example. By the way, you may pose the question that what does it mean that being visited? A vertex is being visited. Okay, if we backtrack and come to the situation that the vertex from where we started, for example, we are going to start from vertex 1, and this vertex from where we started has no more unvisited adjacent vertices, then it will become visited, but until then, it is being visited. So we start at the root node, for example this vertex 1, and it is being visited. We keep visiting its left child in a recursive manner. This is how depth first search works. So we keep visiting the 2. Okay, it is being visited because it has some unvisited neighbors, some unvisited children. So we keep going as far as possible. This is the most important feature for depth first search. And in this situation again, this vertex 4 is being visited. That's what the yellow circle means, that it is being visited. Okay, we have already considered this vertex, but it is being visited at the time. So in this situation, for vertex 1, it is being visited. Vertex 2 is being visited. Vertex 4 is being visited. Then we are going to consider vertex 8. It is being visited, but then we come to the situation that it doesn't have any children, so in this case it is not being visited. We set it to be visited. We have already considered the vertex 8. Okay, so I set it to green, for example, which means that we have already visited it and we are not being visited it anymore. So set visited true, set being visited is equal to false. Then we backtrack to the parent, which is the 4. And the 4 is being visited because it still has some unvisited neighbor, the vertex 9. So we keep visiting the vertex 9 and we come to the situation that it doesn't have any children, so we consider it to be done. So that's why I colored it green. All the green nodes are visited. We are no longer considering them, so they are not being visited anymore. But the vertex 1, the vertex 2 and the vertex 4 is still being visited. So we backtrack to the parent of 9, which is the 4. We come to the conclusion that the 4 doesn't have any unvisited children. Okay, it has the 8 and the 9, but we have already set them to green. So it means that it doesn't have any unvisited children, so we consider it done. Okay, it is no longer being visited, it is done. And we backtrack to the parent, which is the 2. The 2 is still being visited because it has an unvisited right child. So let's visit it. We visit the 5. Okay, we consider the 5 and we come to the conclusion that it still has some unvisited neighbor. And we visit the neighbor and we come to the conclusion that, okay, the vertex 1 is still being visited. And there's a backward edge to a vertex that's still being visited, which means that there's a cycle. So I don't want to repeat myself over and over again, but it's very important that what's the difference between being visited and is visited. Vertex 1 is being visited because we haven't considered all the children and the children of its children and the children of its children of its children and so on, because it is a recursive implementation. That's why we call it over and over again on its neighbors and on its children. And in this situation, okay, we have some vertices that are done. The 4, the 8 and the 9. But the vertex 1 and the vertex 2 and the vertex 5 are still being visited. And there's a backward edge to a vertex, here in this situation to the vertex 1, that's being visited at the time. So that's how we can figure out that whether is there a cycle in the given graph or not. In the next video we are going to implement it together. Thanks for watching.